Welcome back. In this lecture, we're going to go in a kind of different direction from what we've previously been doing. Previously, we focused on classification tasks, especially with a little mix of regression thrown in there too. So when we do classification, we aim to predict the value of a qualitative variable, like whether or not someone survived on the Titanic or what the species of a penguin is. In regression, we aim to predict the value of a quantitative variable like average happiness or GDP or revenue over time. These are two of the most common and fundamental tasks in machine learning, regression and classification. However, they are not the whole story. And in this lecture, we're going to take a look at another part of the story and another kind of machine learning task, and this one is called clustering. So clustering fits into the broad set of unsupervised machine learning tasks. Unsupervised machine learning tasks are actually kind of outside the conceptual framework that we started with because there's no target variable to predict. So we have predictor data, X, but there's no predicting variable, Y, that we actually are trying to predict. So this is a bit outside the framework. When we do unsupervised tasks, including clustering, we just aim to explore the data and find some kind of latent structure or pattern that might exist within the data. Now, the most common example of unsupervised task is clustering. When we do clustering tasks, we hypothesize that the data might naturally be divided into dense clusters. So little chunks of data in the data space. And the purpose of a clustering algorithm is to identify these clusters. So let's go ahead and try this. As usual, let's get ourselves NumPy. And from matplotlib, import pyplot and import pandas as PD. Okay, cool. No question mark. Okay, so there we go. The first thing we're going to do is create some synthetic data, and the good folks at scikit-learn have actually made this great and wonderfully named makeBlobs function, which will create a user-specified number of blobs of data, which are all pretty well separated from each other. Let's take a look at what that means. So from sklearn.datasets is where I'm going to get the makeBlobs function. I'll import makeBlobs. And now from here, x and y true are equal to make blobs n samples. That's the number of data points equals 300. Let's make 4 blobs. The number of blobs is controlled by the centers. I'm going to set the cluster STD, that's cluster standard deviation, that controls how spread out the blobs are. Let's make that 0.60. And let's do random state equals 0. So no randomization. And now let's take a look at what we have. So we are going to make a figure, subplots1. And what we're going to do, so the makeBlobs function will give us x as a 2-dimensional NumPy array with 2 columns, and one column gives the x coordinates and the other column gives the y coordinates. So we can plot x by plotting column 1 against column 2 on axes. So we'll do x.scatter x 0 and x 1, and let's make the size equal, let's say 30. So I bring in this data set, this function makeBlobs. I use makeBlobs to create a synthetic data set, and then I visualize it. And I see here that my data does indeed look like it's divided into approximately 4 blobs. So I see that there's kind of a center to each one, and then there are all these points that are spread out around that center, thus making a blob. Now, I can, of course, make my blobs more or less blobby. So if I reduce the standard deviation, I get blobs that are much more clearly separated from each other. They're more tightly packed. On the other hand, if I increase my standard deviation, I can create blobs that kind of run together, and now it's almost not really visually clear that there are any blobs at all. So let's stick with our intermediate value at 0.60. This is a nice value because we can see that the blobs do run together a little bit, but not too much. And we can do some experiments later to see what the result of increasing or decreasing the standard deviation is on how these algorithms perform. That's a great exercise for you to do on your own. So for now, here are our blobs. We're going to play with this data. And what we do is we import the k-means function, just like we would any other function. Okay, actually, before we do that, there's one other point I want to raise here. Notice that when I did make blobs, I actually had this vector y true. And I can plot the blobs with colors distinguishing them by y true. And you can think of these as the true cluster labels. So I can see that my blobs are actually meaningfully separated, but with the true cluster labels. Now, here is a good point for you to be complaining, because didn't I just tell you that in unsupervised machine learning, such as clustering, we don't have true cluster labels. There is no y true. And this is correct. There's only a set of true cluster labels when we generate the data ourselves, okay? So only when we create fake data. When we have real data, there's no y true that goes into our training algorithm. And so in this case, we can have a y true because we got it from our synthetic data generation, but we're not going to use it in any of our algorithms. We're not going to be using any training y true or any testing y true. Y true is not going to show up in our machine learning pipeline. It's just an artifact of how we artificially generated our data. Okay. So now let's go ahead and make our k-means model. So we are going to grab k-means from sklearn.cluster. So that's the place where we can get a k-means model from sklearn.cluster, import k-means. Now, fitting a k-means model is really nice and easy. So I'm going to start with a k-means model where n clusters is equal to 2. So this says, hey, I want you to find 2 clusters in the data. And we'll do k-means.fit x. Okay, so we load in that function, we create an instance of the model, and we call the fit method to fit it to data. This is exactly the same pattern that we've seen many times now. We can get the cluster labels, so y k-means. So notice now that y is not something that we use when fitting the model. When we fit the model, we only used x here. Okay, but we can now get the cluster labels that the model has given. So we get y k-means from k-means.predict x. Okay, nice and fast. And we can go ahead and visualize the results. So we can actually use exactly the same code we took from up here, but instead of using y true, that fake part of the, that fake set of labels that we got because we generated the data synthetically, we can use y k-means, which is what the k-means algorithm thinks the labels should be. And okay, so this is kind of interesting. So if we take a look at what we have here, we can observe that the k-means algorithm with 2 clusters, it looks like it's more or less identified one of the clusters, that's the yellow one up here, and then it's grouped the other 3 clusters all together, and it thinks that they are a single cluster. So that's, you know, an interesting outcome, but not great. Let's see if we can improve it. Now, since we have the benefit of being able to inspect the data, and since we say, hey, it looks like there might be 4 clusters in this data, let's make a change. So we initialized the k-means model with 2 clusters initially. Let's change that to 4 and run our code again. And this time we get a much better result. So notice here, we've actually successfully recovered the 4 clusters. So each of these clusters has a different cluster label that's reflected by a different color in this visualization. We can see that k-means was actually able to detect the 4 clusters quite effectively. Now let's take one more step and notice what k-means is kind of doing actually in order to make this happen. So the 2 principles of k-means are as follows. First, there exists a centroid of each cluster. So the centroid is just in the middle of the cluster, and the centroid is the mean of all the points to which it corresponds. Furthermore, each point is closer to the centroids to which it corresponds than to any other centroid. So we say, hey, for each point, which cluster are you in? And then we say, okay, well, you have to be in the cluster whose centroid is closest to you. And furthermore, that centroid has to be the mean of all the points in that cluster. So there are these two conditions for the k-means model. And the k-means class makes it very easy to grab the cluster centroids, and then we can visualize them, which is very handy. So let's take a look at visualizing the k-means centroids. So we'll do centers equals k-means.cluster centers here, x, and then we're just going to scatter the centroids in a different format. So we'll do centers. So similarly to x, the centers are given as a 2-column set of data. So we plot one column against the other to get a visualization on horizontal and vertical coordinates. I'm going to plot these kind of larger and a little bit transparent on the same axis, and then I'll take a look at the figure. So these slightly transparent black circles show you where the centroids are for each of these data sets. Okay, so for each of these clusters. So what this is telling you is that, hey, this black circle, that's the middle of the yellow cluster. The black center over here is the middle of the dark blue cluster, and so on. So this experiment went pretty well. We had a false start in which we chose not enough clusters, and so we didn't do a very good job of detecting. Then we increased the number of clusters, and we did a pretty nice job of getting the data that we need. Of getting the result that we need, finding the clusters in the data. Now, this experiment went very well, but real things in the real world are never quite that easy, of course. So let's take a look now at the Palmer Penguins data set. So I've just pasted in here my usual functions for retrieving this data. And let's make a scatter plot, something like you've made before. That will plot the Kalman length against Kalman depth for the penguins. So for S in, let's make a new figure. So fig x equals plt.subplots1. Now for S in penguins, species.unique. So I'm just going to loop over the possible species of the penguins. This code should be pretty familiar to you from a recent discussion section. GF equals penguins. Species equals S. So my little temporary variable df is just the part of the data where the penguin species has the current species value. And then I'm going to scatter df and length mm and depth with label equals S. So of course, let's see here. I did not do a good job of spelling. And where is that? Oh, right, it's because I forgot to close my brackets here. That should be better. There we are. So, of course, in real life, I should label my axes and I should add a legend for my different species. But just looking at this picture here, we can see some promising things. So if I look at this, I might say, oh yeah, it looks like there are some clusters in my data. Maybe I can use k-means to figure out the different penguin species by clustering them along Kalman length and Kalman depth. Now, this is a pretty logical idea, so let's see if we can do it. There are maybe some clusters here, maybe there are even 3 clusters if we're lucky, so let's take a look. So what I'm going to do is I'm going to make my x variable. So my x variable is just going to be these 2 specific columns of the penguins data set and Kalman depth so that's what I'm going to cluster on. And if you remember in this data set, there are a couple of NA values in these columns. So I actually need to drop NA values here as well. Then k-means equals k-means and clusters equals 3. I'm being optimistic. I'm going to say, hey, maybe there are 3 clusters in my data set. Can we find them? And I'll do k-means.fit of x. Okay, so that runs pretty quickly. So we now have some k-means clusters for our penguins data set. Let's give it a shot. Fig and x equals plt.subplots1. Let's see what we found. So I'll scatter, similarly to before, x Kalman length on the horizontal axis, X Kalman depth, on the vertical axis, and my colors will be k-means.predict X. So those are the clusters that my k-means model has guessed for the penguins data. Run, and oh dear, those are not the right clusters really. So it looks like on the top left, this kind of dark green cluster, that corresponds reasonably well to the blue cluster from above. So we haven't completely failed. But we've also obviously divided the yellow and purple clusters in completely the wrong way. So we've completely failed to find any kind of corresponding difference between those two species on the basis of Kalman length and Kalman depth using the k-means algorithm. So there's a reason that k-means doesn't really work here. And that's because k-means works best when the clusters are roughly circular. On the other hand, if you look at the clusters in the penguins data set, they are elliptical and they're also kind of diagonally oriented with positive correlation. And this is a problem for k-means because k-means doesn't like either of those. It doesn't like ellipses and it doesn't like diagonally oriented clusters. And so k-means doesn't really have the ability to find clusters in this data set due to the geometry of the data. Now, there are much more sophisticated clustering algorithms. K-means is the OG clustering algorithm, but it's no longer state of the art by any means. So there are many more sophisticated clustering algorithms that can handle data with this kind of structure. We're not going to focus on them in this class, but I have given you a pointer at the bottom of these lecture notes to an example of a more sophisticated kind of clustering algorithm in case you would like to learn more. Okay, so thank you for joining today our discussion of clustering with k-means. In the next couple lectures, we're going to zoom out. And instead of thinking about specific tools and specific components of the machine learning workflow, we're instead going to look at two case studies where we actually apply some of our techniques to two pretty different kinds of tasks where we aim to predict and learn about some real complex data sets. Okay, thanks.